So in this last video, I want to talk a little bit about the runtime of Kruskal's algorithm and one last kind of optimization we want you to make on your implementation of this disjoint set structure. So first, to talk about Kruskal's, we haven't quite analyzed the runtime yet, and that's going to be a useful thing for us when we want to think about comparing Kruskal's and prims. So to kind of go through this, we start with some kind of O of V operation to initialize our disjoint set. We have to make an individual set for each one of our vertices. And then we have to sort all the edges by edge weight. Now, we haven't quite talked about sorting yet, so you're just going to have to trust me on this. Most sorting algorithms take time that's n log n for their input size n. And so since we're sorting a list of edges, that's going to end up being something like e log e. So that's just going to be the runtime for that. Don't worry, we'll understand why sorting is this n log n problem in a couple weeks when we get to talking about sorting. So you're just going to have to take that as fact right now. And so now when we go through the rest of the algorithm, we're going to have this iteration over all of the edges. So we're going to do a loop e times. And then we do all of these kind of operations on disjoint sets. So we have something like log v finds, and then this kind of if statement for if we want to join the two together. Well, that can only happen at most v times because there's only v minus 1 edges in our minimum spanning tree. And so this if statement will only actually enter about theta of v times. And so then we get this kind of like the union, which was also a log v operation. Now, there's a couple things that we should mention here. Didn't we just go through all of that stuff about talking about disjoint sets, about how it could be faster than log v in practice? I highlighted those in pink. So I'm actually talking about the worst case in these things. But in practice, we get this amortized benefit, and so they tend to be much closer to constant time anyways. But this tends to be something that we still have to analyze as kind of this worst case the first time you're calling find. So we end up getting something that ends up kind of adding all these terms together, e log e plus e log v plus v log v. Now, one thing in particular about minimum spanning trees that we didn't quite analyze before, but we have to highlight now, is that in any context, the number of edges is going to dominate the number of vertices. The reason is we can't have fewer edges than vertices, or fewer than v minus 1 edges, because we need this graph to be connected, right? So we can't have the case where the graph is disconnected, there's no edges. We need to have some minimum number of edges. And so in this context, e is always going to be greater than or equal to v, or greater than or equal to v minus 1, but asymptotically, that's kind of the same thing. So generally, we kind of talk about only the case where e dominates v. So you usually see people write this as e log e. Now, why do we do this? There's a couple things. One, we had this sorting time where we kind of talked about this e log e runtime, and that turns out to be the thing that dominates Kruskal's runtime. That's actually generally the slowest part, is the actual sorting. Because those log v factors can sometimes be faster in practice. Now, one thing that people generally do is they generally write this out as e log v. And you're like, wait, where did that e log v come from? And the reason is when you work with logarithms, don't mean to have that there. When you work with logarithms, e and v look more similar. So remember that in the worst case, e is equal to v squared, where you kind of have all these pairs. So then if you think of log e, that's going to be equivalent to 2 times log of v. And so that should... So when you're talking about the log of these sizes, they're within a constant factor of each other because of how logs behave when you have powers. You bring the power down as a coefficient. So log e, log v, they're basically the same or within constant factors of each other. So you commonly will see people write this as e log v because it's the same within constant factors. This is one of the things that's a little bit weird. Everyone has slightly different conventions. So we're going to write down this e log v in our kind of next slide here. But I wanted to mention that like they're equivalent. And that's the reason why you see these differing answers. So this kind of gives us a chance to go back and look at everything we've seen so far. So we talked about traversals, commonly the shortest path problem where we use Dijkstra's. And we got this runtime that was v log v plus e log v. And this is you're going to always want to use this whenever you want to actually find the shortest path in a graph between two nodes. Then we talked about a completely different problem, the minimum spanning tree problem, where we had prims and Kruskals. Now remember, prims is like modified Dijkstra's. You're kind of going vertex by vertex, exploring kind of your known set and adding nodes to it that have minimum cost outside of that known set. So this thing kind of goes vertex by vertex, while Kruskals goes more about edge by edge, where you're always adding things by edges. So even though they're going to end up having the same runtime, E log V, notice we went back and removed that extra term from prims that gets dominated by the E log V term. Prims is going to work well when you have a dense graph, right? If your graph is dense, it has many, many edges, and so it helps you to iterate over the vertices instead. Kruskals is going to be kind of the opposite. When you have a sparse graph, you have few edges, then you're going to be really benefited by iterating over those edges. So Kruskals could be a great thing to apply then. And this is actually one of the cool things is where, runtime doesn't tell it all. That's why understanding how the algorithm works is important, so you can conceptualize why it might be fast in some context versus another. And another really useful context to use Kruskals is if you know your edges are already sorted. So if you have a sorted set of edges already, then Kruskals is going to help you because you can skip that sorting phase and things are going to be really, really fast. So this hopefully gives you kind of a way to conceptualize everything we've seen so far. Now, what I want us to talk about, that kind of last bit of this video, is talking about one last optimization that's going to end up being really useful, which is we're going to do everything as we've done before, this weighted quick union with path compression, but we're going to actually implement it with an array, similar to how we implement a heap. So here's the idea. Because each node only needs to keep track of its parent, we can actually use a super clever representation of an array that keeps track of these parent relationships. So each node in our uptree is going to correspond to an index in the array. And then the value at any particular index is going to store the index of its parent. So for example, since Alex's parent is Ken, the value at Alex's index is 6, saying that her parent is at index 6, who is Ken. And then Ken's parent is at index 0, who is Joyce, which is exactly why we see Joyce here. And so this array representation kind of captures all of these parent-child relationships. Now we need some kind of special value to indicate that Joyce is the overall root, and that we use something like -1. And then one nice thing about this implementation is we get this idea of having a set ID for kind of free, because now we can just use the index of Joyce as the set ID for that set. That's actually one benefit of this. Now, just like with heaps, just like with heaps, we're going to still think about this thing at a high level as being a tree. But in the implementation, we're actually going to be treating it as an array. So it's important to maybe always stand back and draw, what does this tree look like? So now let me show you why we do this, why this makes some of our implementations easier. So now find is the same in theory, but now the details are we have to jump around this array. So we start by having to be able to jump to a particular index for a given person. So just like with our uptrees, we're going to need an extra map to keep track of like where this person is. Remember with the uptrees, we needed this extra map behind the scenes, track, which node corresponds to Alex. Same thing here, where we need to know which index Alex is at. So first thing, we need to jump to that index, and then we need to iterate over the array. And we're going to kind of jump around, jumping to the parent index using the value there until we reach the top. So we go from Alex to Ken to Joyce, using the values there to know which index to go to. Now, once we're at a value with -1, we kind of know that this is the top of the tree, so we can go ahead and return that index. However, now is a chance that we can go ahead and do path compression. Because we know kind of from Alex to Ken to Joyce, and we know Joyce is at index 0 and she's the overall root, we can start over again at Alex and replace all of the things with 0. So replace at the value index 3 with 0, the value index 6 with 0, and leave Joyce as being -1. So you can still do path compression, and this is one of the key reasons why to use an array structure, is it makes it really, really easy to do path compression. You just change some indices. you never have to worry about actually manipulating references and moving nodes around, which is really nice. So no recursion, none of that stuff. You just have to change an index, which is really, really convenient from a programmer standpoint. Now, you can still use other things like union with this array representation, but we do need to be a little bit cleverer with our representation to do things like weighted quick union. So we needed to know for each tree how many nodes are in it, what's its weight. And we could use another data structure to track all of that, but one thing we can do is use the fact that we're storing -1 in each of those array indices for the roots as kind of a storage place for the weight. The idea is instead of storing -1, store the negative weight. So since Joyce has 4 nodes in her tree, we'll store -4 there to represent that it's negative, meaning that she's the overall root. And we use the value 4, the magnitude of that number, is the number of nodes in her tree. And so now we can actually just, whenever we get to the parent indices, just use the value there to know what the weight is. So this is just trying to avoid using an extra data structure. So unioning is exactly the same as before. You just go change kind of the index of one root, the value at the index of one root to be something else. So in this case, because Eileen was a smaller tree, we want to put, excuse me, not sure why I'm coughing so much. We put Eileen underneath Joyce's tree, which means changing the value at Eileen's index from -2, the weight of her tree before, to 0 to say, hey, now they're rooted at this index. Now, one thing I should mention is that using this array implementation does not give you any asymptotic speedups. So with array weighted quick union with path compression, we still get the exact same runtimes. There's nothing asymptotically better here. But there are lots of reasons to use the array here. We talked about before that arrays tend to be faster than link structures because of how memory works. So it's going to be more compact in memory, which means we get better locality. Now, it's not quite as good as our normal usages of arrays where you kind of loop through the whole thing because you're bouncing around from index to index, but it tends to still be better because they're all going to be relatively close in memory because they all live inside the same array. The biggest reason, my argument, is that it also makes the implementation much, much simpler to actually do. It is a bit confusing the first time you see it, but you'll find that the code you write there is much, much simpler than having to rearrange a bunch of pointers using these references. So kind of this much better constant factors and the ease of implementation are kind of the big reasons for why do we use this array implementation. So you'll find that on Project 4 that these slides kind of outlining how to do this are going to be really, really useful when it comes time to implementing your disjoint set. As a reminder, on Project 4, it's going to be challenging because there's so much starter code. So don't worry when you find yourself kind of spending a lot of time reading through the provided code, trying to plan out what you're doing, because that's going to be a huge bulk of the work. Now, you still have to do the coding for Dijkstra's and Kruskal's and disjoint sets, but this is kind of our final project where we want you to get used to working in a larger scope project, which is something you might do if you go out into industry or research or something else. So this is going to be kind of practicing that skill. And so do refer back to these to help you formulate this game plan. That's all I have for us today. I'll hopefully see you in class where we get to practice these ideas.